All right, let's dive into something that sounds kind of intimidating, but is actually the secret sauce behind almost all technology: data structures and algorithms. Don't worry, we're not going to get lost in theory. We're going to lay out a super clear roadmap. Let's do this.
Seriously, have you ever stopped to think about it? Your phone looks at a bajillion possible routes and, in a split second, tells you the absolute best one? How in the world does it do that? Well, the magic behind that little miracle, that's exactly what we're breaking down today.
Okay, first up, data structures. All this is a way to organize your stuff. Think about a library. You wouldn't just dump all the books into one giant pile on the floor, right? Of course not. You'd put them on shelves, sorted by genre, then by author. That system, that structure, is what lets you find what you need fast. That's all a data structure does for information inside a computer. Simple as that.
Now, if the data structure is the organized library, the algorithm is the recipe you follow to find the book. It's the set of instructions. Step 1, go to the sci-fi section. Step 2, find the shelf for Asimov. Step 3, grab iRobot. It's the step-by-step action plan for getting something done.
So, we've got organized data and a recipe to use it, but why should you care? Because this combo isn't just a neat idea, it's literally the foundation that pretty much all modern software is built on. I mean, picking the right structure and algorithm is the difference between an app that feels snappy and one that makes you want to throw your phone against the wall. It's all about speed and efficiency. But it's more than that. Learning this stuff teaches you how to think, how to break down huge, messy problems into logical steps. It's why this is a huge deal in coding interviews, and it's the beating heart of everything from artificial intelligence to your social media feed.
Okay, so let's pop open the hood and look at the actual tools in the toolkit. These are the building blocks you'll be using to solve problems.
First, you've got your linear structures. All that means is the data is in a sequence, one after the other. An array is the most basic. It's just a list. But then you have stacks and queues. A stack is last in, first out. Think of a stack of pancakes. You always take the top one off first, right? That's exactly how the undo button in a text editor works. A queue is the opposite. It's first in, first out, just like a line at the bank. The first person who gets in line is the first one to get helped. It's how your printer knows which document to print next.
But not everything fits neatly in a line. So next, we have non-linear structures. A tree is for anything with a hierarchy, like the folders and files on your computer. A graph is all about networks and connections. You know your social network? You and your friends are the nodes, and your friendship is the edge. That's a graph. And then there are hash tables, which are absolute wizards at looking things up instantly. They use a key, like your username, to find all your profile data in a flash. This is the secret sauce behind so much of the internet. And these are the recipes that put those structures to work. You've got algorithms for searching, algorithms for sorting data, like organizing a video game leaderboard, and of course, graph algorithms. Remember our GPS? It uses an algorithm called Dijkstra's to find that shortest path. See? It all connects.
Okay, so you have all these different ways of organizing and processing data. That brings up a super important question. How do you know which one to pick? How can you tell if your code is actually any good?
And the answer is this thing called Big O notation. I know, it sounds really complicated, but the idea is actually very simple. It's like a report card for your algorithm. It doesn't tell you how fast it is in seconds, it tells you how much slower it will get as you give it more and more data to work with. It predicts whether your code will stay fast or completely fall apart at scale.
Take a look at this cheat sheet. Here, n is just the amount of data. O of 1 is amazing. It takes the same amount of time no matter what. O of n is pretty good. The time just grows steadily with the data. But look down at O of n squared. That's where things get ugly. The time it takes doesn't just grow, it explodes. The difference between good and poor here isn't just a little bit, it's massive.
And this chart says it all. Choosing a good algorithm over a poor one can make your program hundreds, even thousands of times faster when you're dealing with a lot of data. This is why understanding Big O is an absolute game changer for writing good software.
So hopefully you're on board with what this is and why it's so important. The next logical question is, how do you actually learn it? Well, let's lay out a clear, step-by-step roadmap for you. Here's the game plan. First, obviously get solid with a programming language. Then, take the data structures one at a time. And this is key. You have to actually build them yourself, from scratch. Don't just read about them. After that, you start practicing algorithms, figuring out their Big O, and putting it all together by solving coding challenges.
And step 5 is the real secret. You got to do it every day. Consistency is everything. And if you're wondering where to practice, these are the places to be. These websites are basically the gyms for developers. They have endless problems that will take you from the very basics to incredibly advanced challenges. This is where the magic happens.
So, when you boil it all down, what's the big takeaway? Data structures and algorithms aren't just some boring topic you have to learn for a test. They are the practical, logical tools that let you take a cool idea and turn it into powerful, efficient software that actually works in the real world.
So there you have it. You've got the concepts, you've seen the tools, and you have the roadmap. The map is officially in your hands. So the only question left is, what problem will you solve first?